Hello, everyone. In this section, we will introduce LLM engineering using the API from AONet. Our goal is to allow a user to give a natural language instruction, such as take off, and let the language model generate the corresponding Python code, realizing drone's takeoff action in Airsim. Let us begin with the basic idea of prompt engineering. Traditional programming uses precise syntax and predefined logic to control a computer. Prompt-based programming uses natural language instructions to guide the behavior of a language model. Prompt engineering is not simply asking a question. It is a systematic process of designing, testing, and improving instructions so that a model can understand the user's intention and produce the expected result. A well-designed prompt has several important objectives. The first objective is intent alignment. We need to express the user's request in a way that the model can understand accurately. And the second objective is output control. If we only ask the model to control a drone, it may return a long explanation, incomplete code, or functions that don't exist. We therefore specify the required output format and clearly state which functions are available. And the third objective is capability activation. A detailed prompt can encourage the model to break down a complex task, choose suitable functions, and generate a sequence of operations. To design a reliable prompt, we can divide it into several models. Firstly, the role will describe what the model is and what responsibility it has, and the task explain what the model should do when it receives a user instruction. And these constraints define what the model is allowed and not allowed to do. The final model specifies the output format. Together, these modules make the model's behavior more predictable. We also introduced several ways to describe callable functions. The simplest method is a short description. For example, the AW point takeoff would show how to take off the drone, and the land function would land the drone. This format is easy to understand and is suitable for functions that don't require parameters. For more complex functions, the prompt should describe the input parameters and the return values. Error handling can also be included in a function description. Here compares three general approaches for connecting language models with external tools. The first approach is prompt-based control. In this approach, we describe the task and available functions entirely through natural language. It is flexible and easy to complement, making it useful for quick experiments. However, its output is less structured, so additional parsing and validation are usually required. And the second approach is function calling. With function calling, available functions are defined using structured schemas. The language model selects a function and generates structured arguments, often in a JSON-like format. And the third approach is MCP, which stands for Model Context Protocol. MCP provides a standardized way for AI applications to connect with external tools, resources, and prompt templates. It is especially useful when an application needs to integrate many different tools through a common interface. In this section, we will begin with the simplest prompt-based approach. And in the second 2.2, we have already shown how to get the API key from IONet. Now, let us just look at the drone control system prompt. We import the OpenAI client class and provide the compatible API endpoint together with an API key, and the selected model is the Kimi K2.6. The system prompt tells the model that it is an assistant for the Airsim drone simulator. When the user asks it to perform a task, it should return the Python code required to complete the task and briefly explain what the code does. The prompt just introduces an important restriction. The model may only use functions that have been explicitly defined. It must not assume that other functions exist. This restriction is essential, and large language models may sometimes generate plausible-looking functions named that are not actually available. By clearly limiting the model to the functions in our SDK, we reduce the possibility of invalid code. And the chat history will store the complete conversation between the user and the assistant. Every message contains a role and some content. The chat function manages the um, conversation. First, it adds the current user prompt to the chat history. It then sends the complete history to the model through the chat completion API. After receiving the model's response, the function saves it in the chat history and returns the generated content. Saving the history enables multi-turn interaction. After defining the system message, we provide the model with additional knowledge about the valuable drawn functions. In this example, only two functions are introduced, um, just the takeoff and the land. The response may also contain a natural language explanation. And we also define the extract Python code function to execute only the Python code. Now, let us just launch the Airsim simulator. We have already launched the Airsim simulator, and we need to import Airsim wrapper and create an Airsim wrapper instance named AW. This object provides the functions described in the prompt. Finally, we need to execute the generated code. Also, we test another instruction. The prompt is let now Pikachu. This example demonstrates that natural language instructions don't need to exactly match the function descriptions. The language model acts as an interpreter between flexible human language and precise SDK codes. And I will run the code.